Hey, you ever just, watch something totally normal, like ice melting, maybe, and suddenly think, wow, what's the actual science making that happen?
Uh-huh. It's amazing how much is going on beneath the surface.
Exactly. And that kind of curiosity is what we're tapping into today. We've got this great set, feels like somewhere between 20 and 30 of like classic school science experiments.
Right. And even if it's been ages since you've been near a Bunsen burner, these demos show off some really fundamental, um, pretty mind-bending science principles.
Totally. Think of this deep dive less like schoolwork and more like a shortcut to understanding some, well, really core ideas.
Yeah, we've got a real mix here. Stuff looking at chemical properties, observing energy changes, even like the weird ways everyday things like water behave.
Mm-hmm. So our mission today is to sort of unpack these experiments, find the most interesting bits, and really explain the why behind the what happens.
We want those aha moments for you, the kind that make you nod and go, ooh, that's why.
Exactly. Ready to put on your mental lab goggles?
Let's do it.
Okay, first up, testing the pH of oxides.
Okay, so pH, it's basically, a scale. Tells you something's acidic, alkaline, or basic, some people say, or just neutral.
Right. And this experiment uses universal indicator.
Yeah, which is pretty cool stuff. It's like a chemical chameleon, changes color depending on the pH.
A chameleon, I like that. So we add this indicator to different oxides. Let's see, nitrogen oxide, sodium oxide, potassium oxide.
Phosphorus V oxide, calcium oxide too.
Right, and we just watch the color change.
Exactly. Note down the color. That tells you the pH zone.
Mm.
So any gut feelings, what might happen with these different oxides? Metal ones versus non-metal ones.
Mm. Well, you mentioned metal and non-metal. Is there, like, a pattern there?
There often is.
Mm.
Generally speaking, metal oxides, like the sodium, potassium, and calcium oxides here, when they react with water, they tend to form alkaline solutions.
Alkaline, so higher pH.
Higher pH, exactly.
Yeah.
Think blues and purples on the universal indicator chart usually.
Okay. And the non-metals. Nitrogen oxide, phosphorus oxide.
Those tend to go the other way. When they dissolve in water, they typically form acidic solutions.
Acidic, so lower pH, reds, oranges, yellows.
That's the general trend, yeah. It shows a fundamental difference in how these types of elements behave chemically when they form oxides.
Ah, okay, that makes sense. But wait, the notes mention a winkle? What about metal oxides that don't react with water?
Good point. If they don't react, they're not forming those acidic or alkaline solutions.
Yeah. They'd just be neutral. Like, the indicator wouldn't change much from its neutral color, maybe green.
That's a really solid prediction. If there's no reaction producing those characteristic ions, neutral seems likely.
Interesting. It really makes you think about why they react differently, doesn't it? Like, what's actually happening with the atoms and bonds?
Absolutely. It digs into the core of chemical properties.
Okay, moving on from pH to something maybe a bit more tangible, heat. Exothermic and endothermic reactions.
Right. So exit heat goes out. The reaction releases energy, usually feels warm.
Gotcha. And endothermic.
Enter. Heat goes in. The reaction absorbs energy, so it might actually feel cooler.
Cool, literally. Okay, so this experiment looks at a few different mixes. We measure the temperature before and after.
Yep. We've got sodium hydroxide solution plus dilute hydrochloric acid.
Acid and alkali sounds familiar.
Then sodium hydrogen carbonate. That's just baking soda with citric acid.
Ah, the volcano ingredients?
Pretty much. Also, copper 2 sulfate solution with magnesium powder and dilute sulfuric acid with magnesium ribbon.
Okay, quite a mix. So for each one, temp before, mix temp after, see if it goes up or down.
Simple as that. The change tells you if it's exo or endo.
So what should we expect? That acid-alkali one, sodium hydroxide and hydrochloric acid, that feels like it should get hot.
It definitely should.
Yeah.
Neutralization reactions like that are typically exothermic. You'll feel the test tube warm up.
Okay. And the baking soda and citric acid. You said volcano. Those sometimes feel cool.
They do. That reaction is endothermic. It absorbs heat from the surroundings. You probably see fizzing too.
Fizzing, what gas is that?
Carbon dioxide. That's the bubbles in the volcano effect.
Ah, okay. What about the other two? Copper, sulfate, and magnesium.
That's a displacement reaction. Magnesium is more reactive than copper, so it basically boots the copper out of the sulfate solution. That process releases energy.
So exothermic again? Gets warmer?
Yep, exothermic. And the last one, sulfuric acid and magnesium ribbon.
Another acid plus a reactive metal? Feels like that should be exothermic too.
Get it? Exothermic, and you'll see bubbles again.
Bubbles of hydrogen this time.
Hydrogen gas, exactly.
Okay, so we've got mostly exothermic ones here, but one clear endothermic one. But, like, fundamentally, why? Why do some give off heat and others absorb it?
It all comes down to chemical bonds. Think of it like this. Breaking bonds costs energy, and making new bonds releases energy.
Okay.
In an exothermic reaction, you get more energy back when the new, more stable bond form in the products than you had to put in to break the old bonds in the reactants. That extra energy is released as heat.
Ah, like making stronger bonds releases more energy.
Sort of, yeah. And in endothermic reactions, it's the opposite. It costs more energy to break the initial bonds than you get back when the new, less stable or different bonds form. So it has to pull energy in from the surroundings.
Okay. Like an energy deficit it has to make up by cooling things down.
That's a good way to think about it. An energy tug of war.
Cool. Right, let's shift gears completely. This one always seemed weird to me. Water expands when it freezes.
It is weird. Almost everything else shrinks when it gets cold and solidifies. Water's an oddball.
So how does this experiment show it? Sounds super simple.
It really is. Take a bottle with a screw top, fill it completely, like right to the brim with water, seal it tightly.
And then just freeze it.
Yep. Stick in the freezer overnight and see what happens.
Okay, bracing for impact. What's the likely outcome? A cracked bottle.
Very likely, yes. Either cracked or seriously bulging. The ice takes up more space than the water did, and something has to give.
Wow. That's quite dramatic for just freezing water.
It shows the force involved.
And this isn't just a party trick, right? This expansion has real-world consequences.
Oh, absolutely. Burst water pipes in winter. That's this exact principle.
Yeah.
The expanding ice creates huge pressure.
Ugh, yeah. Had that happen once. Not fun. And like milk bottles left on the doorstep in old times, or even stuff in the freezer now.
Yep. Lids popping off containers, plastic cracking, same expansion of work.
The notes even link this to rocks cracking. How does freezing water break rocks? Seems unlikely.
It's a process called freeze-thaw weathering. Water gets into tiny cracks in the rock.
Okay.
Then it freezes, expands, and pushes the crack slightly wider. Then it thaws, more water gets in, freezes again. Cycle after cycle.
Ah, so it's like a slow-motion jackhammer powered by freezing water.
Pretty much. Over time, it can break down huge rocks.
Incredible. Okay, let's talk metals. Transition metals, specifically using copper. There's a copper envelope experiment. Sounds intriguing.
Yeah, it's a neat one. So transition metals are those in the middle block of the periodic table. Copper's a classic example. Wiring, pipes, coins.
Right. So we take copper foil, fold it into an envelope, carefully. Note say sharp corners.
Definitely be careful there. Then you heat this little copper envelope really strongly in a Bunsen burner flame for a few minutes.
Goggles on, I assume.
Absolutely. Safety first.
Okay, heating the copper envelope. What happens? What do we see?
Well, the outside of the envelope will likely start to turn black.
Black. Okay. What about the inside?
When you let it cool down and carefully unfold it, the inside surface will probably still look like, well, copper. Shiny, reddish brown.
So black outside, normal copper inside. What's going on?
The black stuff is copper oxide. When you heat copper in the air, it reacts with oxygen.
Forming copper oxide. Makes sense, but why only on the outside?
Because the inside surfaces were folded over, right? They were largely shielded from the air. Much less oxygen could get in there to react.
Yeah. Limited oxygen supply inside the envelope. Clever.
Exactly.
The notes also ask why copper doesn't just burst into flames like magnesium might if you heat it like that.
Good question. It comes down to reactivity. Copper does react with oxygen when heated, but it's way less reactive than magnesium.
So magnesium reacts much more energetic.
Much more vigorously, yeah. Magnesium can burn with a really bright white flame because its reaction with oxygen is so much faster and releases so much energy quickly. Copper's reaction is more sedate.
Got it. Different personalities, chemically speaking. Okay, staying with metals, but zooming in on group 2, comparing reactivity magnesium versus calcium.
Right. Group 2 metals, the alkaline earth metals. They're reactive, but generally less so than group 1 next door.
And this experiment checks if there's a difference within group 2.
Yeah, it looks at magnesium and calcium reacting with acids. You set up 2 test tubes, same amount of dilute hydrochloric acid in both.
Okay.
Then drop a piece of magnesium in one and a piece of calcium in the other, and observe.
Observe what? How fast they dissolve.
Basically, yeah. Look at how quickly bubbles are produced. More bubbles, faster fizzing means a more vigorous, faster reaction.
Okay, so comparing the bubble rate, what's the expected result? Which one's faster?
You should see the calcium reacting noticeably faster, more vigorously than the magnesium, more fizzing.
So calcium is more reactive than magnesium.
Correct. This demonstrates the trend in group 2 reactivity generally increases as you go down the group. although we're only looking at 2 here.
Interesting trend. And those bubbles. We mentioned hydrogen before with magnesium and acid. Is the hydrogen here too?
It is indeed. Both reactions produce hydrogen gas.
And there's a test for that, the pop test?
The classic squeaky pop test.
Yeah.
You collect some gas, bring a lit splint to it, and if it's hydrogen, POP.
Always fun. And we can write equations for these, right? Word and formula.
Absolutely. For magnesium, magnesium plus hydrochloric acid gives magnesium chloride plus hydrogen, Mg plus 2HCl MgCl2 plus H2.
Okay. And calcium.
Same pattern. Calcium plus hydrochloric acid gives calcium chloride plus hydrogen, Kk plus 2HCl MaCH2 plus H2.
Simple, elegant, shows the pattern clearly. Okay, let's change pace again. Melting and freezing. Seems basic, but there's more to it.
There is. This experiment uses stearic acid, which is just a waxy solid at room temp. We gently heat it in hot water until it melts completely.
Okay, solid to liquid.
Then we let it cool down slowly, recording the temperature regularly, say, every minute.
Tracking the temperature as it goes from liquid back to solid.
Exactly. And you note the temperature when melting starts and the temperature when you first see solid forming as it cools.
And the key thing is plotting this on a graph. Temperature versus time.
Yeah, the graph is really revealing. You heat it, temperature goes up. You cool it, temperature goes down. But
Correct. There's always a but.
during the actual melting process, and again, during the freezing process, you'll see the temperature stays constant for a while, even though heat is still going in or coming out. You get these flat sections, these plateaus, on the graph.
Flat sections. So, like, you're heating it, but the thermometer doesn't go up. How does that work? Where's the heat going?
It's going into breaking the forces, holding the molecules together in the solid structure. It takes energy to turn a solid into a liquid, right? That energy is used for the state change itself, not for increasing the kinetic energy, which is what temperature measures.
Ah, okay. So the energy is busy rearranging the molecules, not making them move faster.
Precisely. And the same happens during freezing, but in reverse. As the liquid turns solid, energy is released as those bonds form, and this release counteracts the cooling effect for a period, keeping the temperature constant at the freezing point.
That plateau is the freezing point or melting point. Cool. Okay, next, diffusion. Things spreading out.
In liquids this time, which is slower than in gases, right?
Much slower, yeah. This experiment shows it nicely. You take a petri dish of water. On one side, you place a crystal of lead nitrate.
Right.
On the opposite side, a crystal of potassium iodide. And then you just watch patiently.
Watch water. What are we looking for? The crystals will slowly dissolve, releasing ions, lead ions, and iodide ions into the water. These ions then start to spread out to diffuse through the water randomly.
Okay, spreading out from their crystals.
So where the lead ions diffusing from one side meet the iodide ions diffusing from the other side, they react.
And what happens when they react?
They form lead iodide, which is a bright yellow solid. It doesn't dissolve in water, so it precipitates out. You'll see a line or cloud of yellow forming, usually somewhere between the two original crystals.
A yellow line appearing out of nowhere, that's the diffusion bringing them together.
Exactly. It's visual proof of those invisible ions moving and reacting.
And there are equations for this too.
Yep, word equation. Lead nitrate plus potassium iodide, lead iodide plus potassium nitrate,
And the formula.
PbNO3 aqueous plus 2Ki. Aqueous gives PbI2 solid, that's our yellow stuff, plus 2KNO3 aqueous.
Got it. The notes mention sometimes the yellow line forms closer to the lead nitrate crystal. What might that imply?
Ah, interesting observation. If it forms closer to the lead nitrate, it suggests the iodide ions might be diffusing faster than the lead ions.
Faster? How so?
Well, if the iodide ions travel further in the same amount of time before meeting the lead ions, the meeting point where the yellow solid forms will be closer to the starting point of the slower-moving lead ions.
Like a race where the finish line is closer to the slower runner's start.
Exactly. It hints at differences in ion size or interaction with the water affecting diffusion speed.
Neat. Okay, time for some chemical cleaning, filtration, but using carbon.
Right. Chemical filtration using decolorizing carbon, often called activated charcoal.
Activated charcoal, hear about that a lot. What's special about it?
It has an absolutely massive internal surface area, like
Mhm.
tons of tiny pores and crevices.
Okay. And the experiment. We filter stuff through it.
Yep. You set up filter paper with this activated carbon in it. Then you pour through things like colored water, maybe ink or food dye or a purple potassium manganese solution, even something smelly like sauerkraut juice.
Sauerkraut juice. Brave. Okay, so what's supposed to happen to these colorful, smelly liquids after filtering through the carbon?
The liquid that comes through the filtrate should be much clearer, much less colored. The purple should be gone or greatly reduced. And hopefully the sauerkraut juice should smell less.
Less like sauerkraut. That would be impressive. How does the carbon do that? Is it like a super fine sieve?
Not quite a sieve. It works by adsorption, adsorption. The molecules causing the color or smell get stuck onto that huge surface area of the carbon.
Stuck onto it, like flypaper for molecule.
That's a great analogy. The impurities adsorb onto the carbon surface and are removed from the liquid passing through.
Wow. And this is used in real life, right? Not just for sauerkraut juice.
Oh, definitely. Water filters for drinking water often use activated carbon to remove chlorine taste, odors, and other impurities. Air filters, too. They're a really important purification technique.
Makes sense. Okay, let's speed things up or slow them down. Rate of reaction. How concentration and temperature affect speed.
Right. This uses a reaction where two colorless solutions, let's call them A and B, are mixed. And after a certain time, a blue color suddenly appears. It's sometimes called a clock reaction.
A clock reaction, I like that. So we time how long it takes for the blue to show up.
Exactly. We do it under standard conditions.
Yeah.
First, normal concentrations, room temperature. Then we change things.
Like what?
We try diluting solution A, making it less concentrated. And we also try warming solution A before mixing. And we time the blue color appearing each time.
Okay, so changing concentration and temperature. What's the general rule for concentration? If we dilute A, make it weaker, does it take longer or shorter for the blue to appear?
If you decrease the concentration, it should take longer.
Longer. Why?
Lower concentration means fewer reactant particles in the same space. They just won't bump into each other as often. Fewer collisions mean a slower reaction rate.
Okay, less crowding, fewer reactions. What about temperature? If we warm solution A.
Warming it up should make the reaction happen faster. The blue color will appear sooner.
Faster when hotter. Why's that? 2 reasons.
Yeah, basically 2 things. 1, hotter particles move faster, so they collide more often.
Yep.
Simple enough.
Right.
2, and this is maybe more important, at higher temperatures, more of the collisions have enough energy, what we call activation energy, to actually result in a reaction. It's not just about bumping into each other. They have to bump hard enough.
So more collisions, and more of those collisions are successful ones.
Exactly. Both factors speed things up.
Makes sense. The notes pose a challenge. How could you tweak this to make the blue appear in exactly, say, 10 minutes?
That requires some fine-tuning. You'd have to experiment, maybe try slightly different dilutions or warm it just a little bit or cool it slightly. You'd adjust the concentration and temperature variables until you zeroed in on that 10-minute mark.
A bit of trial and error based on the principles. Cool. Okay, last experiment for this dive. Using our own breath. Carbon dioxide reacting with water.
Yep, the CO2 we breathe out. When it dissolves in water, it forms carbonic acid, which is a weak acid.
And we use indicators again to see this. 2 different ones.
Right. First activity uses thymolphthalein indicator in ethanol. We add a drop of sodium hydroxide to make it blue first. Blue means alkaline.
Okay, blue alkaline solution. Then we just blow into it. With a straw, maybe.
Gently bubble your breath through it, yeah. And watch the color.
What should happen?
The CO2 reacts with water, forms carbonic acid. The acid neutralizes the sodium hydroxide, the pH drops, and the thymolphthalein should go from blue back to colorless.
Our breath makes it colorless.
Okay.
And the second activity, phenol red.
Similar idea. Phenol red in water. Add a bit of sodium hydroxide to make it red. Red means alkaline for this indicator. Then bubble your breath through it again.
And the phenol red changes from red too.
It should change to yellow. Yellow indicates the solution has become acidic thanks to the carbonic acid formed from your CO2.
Red to yellow this time. So both show our breath makes the water slightly acidic. Why do we add the sodium hydroxide at the start in both cases?
That's just to make sure we start in the alkaline range, so the indicators actually show their alkaline color, blue or red. If we started neutral, we wouldn't see that initial color to watch it change from.
Sets the starting point so we can see the change. Got it. And why isn't the color change instant? You start blowing, but it takes a moment.
Well, the reaction itself isn't instantaneous. It takes time for CO2 to dissolve and react to form enough carbonic acid to shift the pH. Plus, you're adding the CO2 gradually with your breath.
Right. The concentration has to build up a bit. Makes sense. Wow. Okay. That's quite a tour. From pH and oxides through energy changes, water expanding, metal reactions, state changes, diffusion, filtration, reaction rates, and even the chemistry of breath.
It really covers a lot of ground, doesn't it? And they're all things you can, actually do and see. It makes the concepts much less abstract.
Totally. We saw how metal oxides tend to be alkaline, non-metals acidic. We felt the heat or lack of it in exothermic and endothermic reactions tied to bond energy.
We saw the sheer power of water expanding when it freezes, witnessed copper reacting, but not too violently, compared magnesium and calcium,
Uh-huh. Watch that melting plateau on the graph, saw diffusion create that yellow line, used carbon to clean things up.
and manipulated reaction speeds, saw indicators change color just from breathing. It really reinforces how these fundamental principles are everywhere.
These aren't just dusty experiments, they're like little windows into how the world works, chemically and physically.
And hopefully listening to this has sparked some of those aha moments for everyone tuning in. Science is tangible, it's observable.
Definitely. So as we wrap up this deep dive, maybe take that curiosity with you. Look around, see a cracked pavement after winter. Maybe you'll think about freeze-thaw weathering.
Right, or mixing baking soda and vinegar for cleaning, that's your endothermic reaction, maybe producing some CO2 gas.
Yeah. So the final thought to leave you with is, what other everyday things are happening around you right now? What seemingly simple stuff might have some really fascinating science just waiting for you to notice and wonder about?
Keep looking, keep asking why.
Absolutely. Thanks for exploring these experiments with us today.